What do you guys want to start? Yes, sir.
1H.
1H. All right, so take a look at 1H.
Can I have one of the practice tests? Do we have any more?
Yeah.
Thank you.
So 1H.
Oh, and 5 is all extra credit stuff.
1H, huh?
And 5 is all extra credit stuff.
No.
That was
Good.
all 3.0.
No, it wasn't. No. Page 265. Wait a minute, let me make sure. Yeah, it's the review. So chapter 3 review. Yeah. So I just left yeah. All right. So what's the trouble with 1H? Let me write it with all this extra. Alright, so that tangent is a power on the 3, and the 3 is inside the natural log.
Can't you bring tangent out?
And I have just given away a huge thing. Yeah, so this is that can come out. Natural log of 3. This is a constant. Good. So the only thing you have to differentiate is that guy. You know what rule is going to happen. You guys with me? That gets really gross. Really gross if you don't bring that down. Oh my God. Then you have a function inside of a function inside of a function. Oh God. Plus you got to differentiate 3 to that, which has its own element of 3. And oh my God, dude. That explains why that's there. Because it would be there anyway. You guys kind of with me? Alright. Is that good enough?
Yeah, I just didn't take the shortcut and I wanted to.
Because it got the whole thing worked out. Alright. Yes.
EMF on 4.
Oh, good. So in the homework, there were these problems that were just like this, right? So you know I'm going to give you one of these on the test. We didn't do a lot of this in the classroom because it's well, we'll see. I was really waiting to see if anybody had questions about it because it should be pretty straightforward. They get a little bit freaky, especially when I'm making the questions. So the very first thing you want to do, real quick, is if I give you the position function, what are you gonna just want to do with that bad boy?
Derivative.
Yeah. If I take a derivative, I get what?
Velocity.
Beautiful.
Negative 3t squared plus 16t.
Yeah. Thank God it's just polynomial, right? I can make it whatever the hell I want it to be. I actually try to make it so that nobody was dying from the forces, the G-force, and I tried it because one time I had like a problem where there were people escaping, and it was some time they died basically because of the G-force, and somebody pointed out like, good, extra credit for you, noticing I killed people.
Negative 6t plus 6.
That's easy. So part E says, at what time does the train stop to head back? So that head back thing is really...
Acceleration is 0.
Yeah, so
When velocity is 0.
when velocity is 0, that means it's stopping. So if I throw this up in the air, when the velocity is 0, that means it could be turning around. Now, it could also just be going, and just keep going. In that specific case, it doesn't do that, right? So I want to know when's the velocity 0. And that you can factor really easy. You don't get fantastically yummy integer answers, but who cares?
But it says when, and then it heads back. Does that have anything to do?
Well, it sort of does. This is what kind of a thing? What kind of a thing is this? It's a weird question, but if you graph this, it looks like a parabola. So where there's a horizontal tangent line, it truly is a turning point, right? Can somebody come up with a function that has a horizontal tangent line that isn't somewhere where it turns? Let me say that again. So this is obviously you might get into you might get stuck thinking that anytime there's a horizontal tangent line, it's going to turn. But that's not true. No, EX never has a horizontal tangent line. Only in the limit that it goes to negative infinity, it never gets there. So
Acceleration.
Yeah, who said starts with a C?
Cubic.
Cubic, totally. Cubic is the evil guy. He says, I'm a parabola. No, I'm not. Right? So there's a horizontal at 0. The derivative is 3x squared, so at 0, this bad boy certainly has a 0 slope, right? But does it turn? No, it actually keeps going.
So wouldn't that be true for all odd exponents?
Exactly. So now you can kind of expand it on, but then there's functions that aren't related to that have that happening to them. You with me? So we are going to develop a general rule, a general, what do you call it, Jeff? You could do it. Thing that we do to investigate whether horizontal tangent line means it's actually turning or not. The simplest thing is if you know what it looks like, you know what it's doing. This is a down parabola. I know it's going to turn when it becomes 0 slope. I don't have to really do much investigation, right? Test. That's a good thing to call it. We're going to develop a test to see if the points where the tangent line is 0, to see if the slope is 0, to see if it actually is a turning point or not. How are we doing? Is that all right? You guys all right? You guys look a little stunned. I had trouble with my grammar on that one, but
So
it's true always.
Is it going to be the same answer?
What's up?
When it says, when it heads back, is it going to be the
Oh no, there's only one answer there.
There's only one answer. So it's going to be the same.
So if I had a more complicated function, I could say, at what time does a train stop? And then I can have another question: is what time is a train headed back towards the base? Because it could be, because it can stop here and keep going. I could have a function where it could stop, keep going, but then turn around eventually. And this would be at what degree? Possibly 4th degree. Looks like it because it's got the right end behavior. Some kind of 4th degree or 6th degree or something. You guys kind of with me? So I could ask you, at what times is the train stopped? And then at what times is the train headed back? Those might be two kind of different answers. On this one, it's the same thing. What time does it stop to head back? Is the way I could have said it.
It would be heading back when it's negative, right?
Yeah, exactly. When the velocity is negative, because I've kind of defined velocity positive when it's going away. Kick ass. I like it. Maybe. All right. Let that be not too weird. I like the wording in 4F. Yeah, I know. It's not really why I like it, but I like a problem like part F because you have to use multiple levels of derivatives that you've done, right? So how fast the train is going, half an hour before it gets back to where it started. So, yeah, I want to know how fast the train is going. So the question on 4F is something about the velocity, but I don't know what time. So there's two things I kind of don't know. I don't know what the velocity is, and I don't even know what time to plug in there. So a really good place to start is, what the hell time is it talking about? Half an hour before I get back to where it started. So if I can figure out what time it gets back to where it started, I can figure out half an hour before that, and then I can just plug it in. That's the process here. It's a multi-step problem.
Circles in a circle?
Yeah.
No. What's happening? So, no. How do I figure out what time it gets back to where it started?
It gives you a range.
So it's not going in a straight line.
0 is less than or
Is it? It's not going in a straight line because if it was, then it would never go back. To where
Well,
it
of course, it's this is the velocity it's turning, and actually this, I know it's cubic, but it's down cubed, right? So at some point in the middle, it's doing something like that, and then it's gonna. Well, that's too many, Jeff. It's down cubed, so it's going like something like that. All right, so here's a maximum. So we come in somewhere here, it goes, and then it comes back. And it's only good from 0 to 8 anyway, so that's why I don't even see any of this other stuff. Right? It's only good from 0 to 8 hours. So I know it's a down cube, so I know it looks like this end behavior-wise, right? And in this work, I can see places where it looks like it probably goes somewhere and comes back. So that's the question. And actually at 0, it starts here. So it does some weird, funky thing, and then it comes back. Now, do you have to know that going in? No. How do I figure out when it's back home? How far away from home is it when it's home?
0.
So its position should be 0. So the first part of part F is what time is it back home? So I'm dealing with this function here, right? Where is it? At what time is it 0 away from home? So how do I figure that out? No, that would be where is it at time 0? Find out where it equals 0. I want to know the time. I don't know the time. When is it home? When is this 0? It didn't say at time 0, then I can make t equal to 0. Much easier problem, much less interesting. This is what the hell time is at home, and then in half an hour before that. Now, of course, it's home at time 0. That's why I know it's home. So at time 0, this bad boy is at position 0, right? So, of course, one thing I'm going to get, how do you factor this?
T squared.
Yeah, take out a negative t squared.
T minus a.
So it's at 0, it's at home, of course, and then it goes away, right? And this little mama cries, oh. And then what time is it back home?
8.
8 hours later, it comes back home, and she's like, oh man, what the hell? You're gone. I've redone your room.
So half an hour would be like
Well, isn't that the same as the range that they gave us?
Yeah.
It just happens to be.
Okay.
Not saying it always is that way. But that might be why I decided to make the range that way, but the range could be independent of that. Maybe the home station is in the middle and it goes, comes back, and then it keeps going. So the range might be further. You kind of with me?
Yeah.
All right.
So if it's half an hour,
So then the
Good. So if it's 8 hours by the time it gets back home,
7.5.
so now I'm curious about at 7.5, at that position, how fast is it going? Just plug 7.5 in. It's a multi-step problem.
You plug 7.5 to the velocity?
Yeah.
Or
So the two steps I needed were, if I could only know what time it was talking about, so I got to figure that out, then I could plug it into velocity and figure out how fast it was going, right? So this was to figure out what time it's talking about, half an hour before this. And now that I know what time it's talking about, I could plug it in and see how fast it was going. Yes?
Was the question, what's the velocity when the particle equals 0?
Do you have a copy of this?
Yeah.
Okay.
Wait.
So 4F. How fast the train's going, half an hour before it gets back to where it started. No.
So if it's negative, that means what?
It makes kind of sense, because positive velocity is defined to be going away from, so that would be here, and then negative velocity is when I'm coming back. I like it.
So that's what you leave your answer in a negative form?
Yeah, oh yeah, definitely. Yeah, that's fine. If you didn't put the negative, I'm not going to kill you. Right? I'll just maim you. Negative for velocity has meaning. It means the direction away. So on some of the problems you weren't terribly careful, or it didn't really matter, because you're just talking about the speed. If they say, what's the speed? I don't need a sign. Don't tell me you're going negative 40 mile an hour. I don't know what the hell that means. Right? Are you Buckaroo Banzai? Going into the 8th dimension? No? Nobody got that far. But on this one, it definitely has meaning. Am I going away from it? Am I coming back to it? Right? It's the direction I'm going. Okay? Anything else? It's a quick day. Yes, ma'am.
Can we go over implicit differentiation?
Sure. So, do you have a specific problem you want to look at, or?
No, just the whole concept.
So if I have a function, some function's given to me, and let's just say f of x equals y, and I want to know what dy dx is. Well, that's going to be df dx, but one way I can rewrite this is df, if I want to know dy dt, let me say it like that. That would be df dx dx dt. Now this is really kind of weird. But this is kind of like the chain rule piece here, right? So what do I mean by this? So if I have, this is related rates, which is sort of like implicit differentiation. So implicit differentiation is even more basic than related rates. It could be any variable I'm taking respect to. So something like, let's start off small here. So if I had, what you got, Jeff? E to the y equals tangent of x and y. I like it. Nice and gross. So the reason I have to have something like implicit differentiation is because I cannot get y by itself, or x for that matter, easily, right? X I could sort of get by itself, take inverse tangent and then divide by y. I actually could get x by itself, but we won't. Let's pretend like we didn't see that. In fact, I'll do this. Not to just do it. So the idea, of course, is y is a function of x. X is x. So when I take a derivative of something with y in it, so what's the derivative of e to the 3x minus 2? What's that guy's derivative? Yeah, why is it times 3, Tori?
Because it's a derivative.
Tori? Chain rule, beautiful. Because I have to multiply with the derivative. So what did I just do in general? I could have just put any function up there I wanted to, right? Then this derivative would be e to that times the derivative of that with respect to x, right? Cool. This is implicit differentiation. Instead of making a specific explicit function up there for you to look at and sink your teeth into, I'm just saying it's some function y. I don't know what the hell it is. I don't know what y is. But it's a function of x. So what's this saying? When I take a derivative of e to some function, it's itself times what? dy dx. Just like you did here. That's d this dx, isn't it? So it would be times dy dx. How we doing? You guys alright? That's key. I think most of you guys seem to be okay for the most part with implicit. But let me do this again. If I did this, what's this guy's derivative? Times the derivative of this, right? Now what could I have put up here? Knowing me, anything. Knowing me, weird, ugly shit, right? But anything I want to put up there, let me just make it y. Like what we got. Its derivative is going to be e to the y, and then this guy gets a turn, right? Cool. That's the idea. That's implicit differentiation. Instead of actually having something I have to take a derivative of, I just have the letter y that I have to say, take the derivative of that. Somebody else, because I don't know what it is. We don't actually have to do it. There it is. Yay. And then what's the other side become? I'm sorry, somebody have their hand up?
Secant squared x y.
What did I say?
I don't even study at all.
Times the derivative.
That's awesome. That's America right there. I'm proud of that. I don't want facts getting in there and messing up with my beliefs. So this is I forget. I think it was your favorite thing. You with me? So the same way I had an inside function there, I've got to take a derivative, and I've got to take a derivative of xy. How do I take the derivative of xy? Product rule. Derivative of x is 1, so we get y. 1 times y plus x times derivative of y. What's the derivative of y? dy dx. So really, I am always doing d something dx. But dx is just freaking 1, right? It's just 1. But then I got plus x dy dx. Is dy dx 1? No. And now you would just get you would distribute this, get your dy dx stuff on one side. Is that cool? Now it's algebra after this. Yeah.
This is a question for G on question.
Did anybody have anything else on this here?
You could have taken the ln of both sides.
Oh, sure, yeah. I could have taken ln, but then I would have had an xy inside of a tangent inside of an ln.
Well, it would have been 1 over tan, right? Which is the same as cotangent.
But I'd have an ln of tangent of xy. So I'd have 1 over tangent times the derivative of tangent times the derivative of xy. All right?
Yeah.
I like it. I'm sorry, so 1g?
Yeah, no, I was just wondering because some of the problems on the homework were saying to use the law of
Oh, yeah.
Would you want us to do that for this?
Only if I said.
Okay, so we just use product rule for this.
Yeah, you could just use product rule for
Okay.
that. Cool. I like it. Because if you use ln, you can make it a plus and you can bring the powers down.
Right, that's fine.
But then you're kind of making all the work in getting like denominators if you had to move forward.
Right.
So if I wanted to see where the horizontal line, the tangent line was horizontal, I'd want to do it like that. Because then I can factor it easily.
Right.
Yeah.
So you wouldn't ask us like to find the horizontal tangent if we were given like a natural log problem like that, or yes?
Oh, totally. Yeah.
Okay. Okay.
Gotta be ready.
Into H?
Oh, we did H. 1H?
Yeah.
Yeah, we did 1H. You bring that tangent down.
Okay. Oh, okay.
Well, here, let me do this. Everybody's asking questions for practice. Let me go ahead and give you that answer key. And then we'll do the few that I didn't put on here. There you go. Cool. We figured it out. Yummy.
So for 3, we can't use the derivative to find the increase and decrease you want us to graph. I mean, you asked for that, right?
Yes, I'm trying to make a problem like given this graph, draw f. Given a graph of f, draw f prime. Now, obviously, if I give you the function, you can kind of on the side do the derivative and make sure that your end result looks like it.
Okay.
Cool. On the test, please understand, I am probably going to give you a function, a graph of a function without its definition. And you're going to have to graph, just like section 2.8. So I'm going to give you, and then you have to come in and on top of it graph the slope.
Which this one should just be like a parabola, right?
Yeah, you know the derivative of this is going to be parabolic. Yep, so it should be parabolic. Cool. But just make sure when you do that, you have to really be clear about where 0 is, you know, your anchor points. And I say explain your reasoning. So you're going to have to tell me it's got positive slope from here to here, so that's why it's on the plus side. All right, I don't understand some of you guys. This is, just throw your questions at me. Some of you guys are looking at me like, what the hell? I got nothing. I got nothing for today. Nothing. I did this, that's all, that's enough for me. Yes, sir.
Okay, so it's the 101 and 102.
Was that the one? Yeah.
It's the
102 I left off of there, and 104 I left off of there. Just because I ran out of room. Where are you? 101?
yeah.
The one about the sun?
Yeah.
I like that answer. It looks cool. And I started doing it one way, and then I decided there was a better way to do it on the answer key.
The angle of the sun.
So, take a second and try to draw this. It says the angle of elevation of the sun is decreasing. Let's see, at a rate of 0.25 radians per hour.
So that would be d theta dt, right?
So the symbol here would be d theta dt. I like it. Can you draw that picture? Maybe throw a building in there too. I like it. And you got room for a building. But where's your angle? Where's theta? That's the important part of your drawing, is put theta in the right place.
So theta's here, the sun's here, and then you have a triangle.
What number is this?
101 on 267.
So when they say angle of elevation, that's the angle that you have to actually rotate your head up, or just your eyes, or whatever the hell you're doing. Right? That's the angle you actually have to lift. So you always start horizontally. So if you're in a plane, and they say the angle of depression to the person on the side of the cliff, that's how far you have to move down. The angle there, that angle. So this is, I'm on the ground. I have no idea what kind of limbs in there. And here's the sun. So this is the angle of elevation, right there. Let me throw a building in there. All very much to scale. And I'm underneath the ground, just so you know. My eyeball's right on the ground. All right. Anytime I see a building, I just got to bury myself. They scare me.
Cemented into the streets.
Okay.
Or you could be like creeping on somebody's house.
Yeah, I got Spider-Man problems sometimes. That sounds weird. I got Spider-Man problems. All right. So do you guys understand? I put the building here. The reason that anything has a shadow is because of this idea. The sun does not get here. It goes right over the edge there. That's why a shadow exists. Right? It's a good thing to know. But it's good to kind of, sometimes that's lost. And I don't blame you too much because you never think about it this way. How do I draw the picture to represent the shadow and the sun and the angle? Well, this is exactly, we did this with the woman walking towards the street light, right?
So,
and this is how tall?
Closing, right?
How tall is this?
400 feet.
400 feet? Obviously.
So the other ones are just X and Y, right?
Second?
So the other, like, because we don't know those values, would they just be X and Y?
Which values? So which value am I interested in?
What is the
How fast is the shadow cast increasing when the angle is something specific? So which part am I interested in? Good. I'm interested only in this. I don't care about that. So I'm not even going to label that. I don't need it. Only if I need it do I then give it a label. Does that make sense? Because otherwise you're going to try to incorporate. You don't really need it. Why do I not need this? Why do I not need this side?
Because it has nothing to do with tangent.
Well, tangent is there. I can relate what I know, what I want to know something about, and what I know something about. I can relate them already with a function. I don't need this guy's help. Does that make sense?
But wouldn't you need it to find the value?
No, I don't. If I want to use Pythagorean theorem, but that's not, then it wouldn't involve the angle. And the angle is the most important thing to have. It's the only thing I know anything about, the rate.
Okay.
So what relates what I want to know something about, what I know for sure, and what I know how it's changing is tangent.
Okay. Understood.
And we'll see, there's an even better way, because I started going the tangent route, and I realized, no, it's going to get a lot grosser than it needs to be. If you do tangent, what's it going to be? 400 over x. Right? And then you got like over x, and then you have a derivative that still has x in it, and it's just disgusting. Whereas if you use cotangent, what's that going to look like? Yeah, 1 over 400 times x. Even a better way to look at it. X over 400, right? And then that derivative, is there going to be any x's left alive? So what I did was I started here, I brought the x up, I took the derivative, and then I had to know what the value of x was at pi over 6, and that's kind of gross. And then I realized, holy shit, if I just do this, x goes away. I just get dx dt, that's all I want. I don't want to know x. I don't know x. I don't want to figure it out if I don't have to. I don't know if you guys are with me. So if you did this and you worked it out, you would be fine. It would just be a little harder than it has to be. And why is this okay? Because what's the derivative of cotangent? Negative cosecant squared. d theta dt. And real quick, what should this really be? 125. Equals?
Negative. Square is decreasing.
So again, let me slow down a bit, because the most important parts of these kind of problems are
Drawing the picture.
What's the picture? What are my variables? Don't assign too many variables to things. You're gonna feel, if you put a z here or something, you're going to feel like you're supposed to use it. There was nothing in this problem that said I cared about hypotenuse. I don't have to use Pythagorean theorem, right? So what do I know something about? It's got to show up. What do I need to know something about? Dx dt, that's got to show up. And then the building, thank God, I know how tall that is. It's not changing height, right? As you get closer to it, it grows taller. Yes?
Where did the x over 400 go? You took the...
It just flipped. It become 400 over x becomes x over 400.
I know, but like, because once you take the derivative of x over 400...
Oh, I'm not done with it yet. I'm sorry. This is this side.
Okay.
Equals.
Okay.
Your 400.
Well, you have to go there. Yeah.
1 over 400 dx dt.
Yeah.
See, did I get that?
I guess you could leave it there.
Oh, I left the 400 on the other side. All right.
Yeah.
That works out. And now the really nice thing is, they tell me what angle I'm curious about. They want to know when theta is pi over 6. And real quick, just to, a part of this is, if the sun does go down just a little bit, so now the rays are like this, what's going to happen to the shadow? Of course it's going to get bigger, yeah. So that's why, as the angle's decreasing, this side should get bigger, so it should be increasing. So the sign of my answer should be positive. And we got a negative there, and this is negative. Hey, sweet, all right, good. Maybe. And now I just got to throw stuff in. What's cosecant of pi over 6?
1 over sine of pi over 6.
I like it. And what's sine of pi over 6?
That's
Sine of 30?
1 half.
Beautiful. Sine likes y. This is nowhere near y, so it's small. It's like, oh shit. So this will be 1 over 1/2 squared. 4. Kick ass. So it's negative 4 times negative 0.25, which is 1/4. Kick ass equals 1 over 400. That's really nice. And then, of course, you end up with the funny thing is, the rate at which this length of the shadow is increasing is exactly the height of the building per hour. It's kind of nifty. So how many of you guys actually try that problem? I don't know if anybody had time to try that problem. Anybody try that problem? Right, okay. All right. Oh, 102? Okay, let's do 102 because they didn't put the answer on the key.
Oh, you just have to remember the point.
Yeah, what's the... Again, if you forgot it, you didn't forget it. Because, of course, we know that y minus y1 equals m times x minus x1. So y equals m x minus x1 plus y1. So f of x, what I think the book calls the linearization of x. So it makes a new function out of it. So we're going to come up with a line that approximates the function close to some value a. So this is equal to m, which is what better known as
The derivative.
the derivative at the point times x minus the point there, plus the output at the point. Cool. So you got to know this. And you already came into this class knowing it before we even reached derivatives. So in this problem it says, find the linear approximation to this close to 3. Yeah, near. So this is my a value. Okay. It kind of makes sense. The idea of the tangent line, it should hug my function for a little bit. Right? Now, what kind of function would this not really work well for? What kind of function would you not be able to get very far away from your... Can somebody give me an idea of the kind of function? Remember, let me try this other way. What kind of function would this work perfectly for?
A line.
A line. Yay! Its linearization is itself. It works for negative infinity to infinity.
Maybe a sine function.
Yes, anything that... so if I had something that's not really sloping very much, it's like this. A linearization of this is going to work beautifully. It's going to work for quite a long time, right? Whereas if I have a function like this, right? it's not going to see this piece. It doesn't look like that for very long. Over here, it's actually the opposite slope. Holy shit. So you have to have a really small neighborhood, whereas here you can have a pretty big neighborhood of A and still be pretty close. Obviously, the more linear, the less curved your function is to begin with, the better the approximation is going to be for a longer period, for a bigger interval. How are you guys doing?
Good.
Good. So if you understand that, then you understand the basic idea of every function. I don't care how funky it looks. If it's differentiable, the closer you get to it, the more straight line it is. It's just how long is that straight line close enough to the actual function. All right, that's what they mean by near. What does that mean? It depends on what the function looks like. Nah. So what do I need? I need f of 3. What's f of 3?
4.
Beautiful. 25 minus 9, 16 squared is 4. I also need f prime. What's f prime of x going to be? 1/2.
25 minus x squared times x.
That's 3 half.
Yeah.
Negative
All
1.
right,
Yeah.
let me do this.
It's negative 1/2.
Here's the function. 25 minus x squared to the 1/2. So that now the derivative, the 1/2 comes down, and it goes down by 1.
Negative 1/2.
Now it's times
2x.
negative 2x. All right, let me stop there for a second. You leave that negative out, the whole thing's wrong. So you gotta be careful here with the negatives. It's going to change totally where you are, where you say your function's going. So if I want to clean this up a little bit, what can go down?
25 minus x squared.
Yeah, there's a 2 down there already, so I get 2 times, let's just make it rad. Bless you.
Cancel the 2's, dude.
And then the negative 2x, yeah, cancel the 2's, I like it. Kick ass. So what do I need this for? F prime, yeah, good. F prime of 3. That's going to be beautiful. Negative 3, and we already know this is 3 is 4. So, I mean, the funny thing to me about section 310 is it's just saying find the equation of the tangent line at this point. That's all it's saying. It's just looking at it a little bit differently. So we've done this kind of problem before. We found the slope. We know the point. Now we can make the equation of the line. So then we know that near 3, the square root of 25 minus x squared is approximated by, where did I go? F prime, so the slope, negative 3/4 times x minus 3 plus 4. Yes, and then just cleaning this up a little bit. See what you got, Jeff. Negative 3/4 x plus 9/4 plus 4 is 25/4. Is that right?
Is that 5/2?
So what's the problem say? It says part A, find the linear approximation. That's part A. F of x is approximately that. So at 3, what should the output of this be? It should work perfect at 3, right? So the output of this should equal the output of this. So at 3, it better be 4. That's the one place that the tangent line agrees, because that's the one place that a tangent line meets the function, right? That's what tangent kind of means. It only meets it at that one point. And of course, if we plug a 3 in, I get negative 9/4 plus 25/4 is 16/4, which is 4. Thank God. So you can really quick just check to make sure this is right by making sure it's good at that point. You guys follow. You can also graph it and make sure it looks right. I mean, if your graph is this and your function is that, I'd say that's wrong. Maybe you just got a negative to kind of escape you. All right. Part B says, illustrate part A by graphing f and the other. So that's exactly what it just said. So graph this bad boy. Anybody know what this looks like? It's not parabola.
It looks like a...
Well, you guys can do it. Watch. Y equals this. Square both sides, add x squared. What is that? Circle. So rad number minus x squared
Not circle.
is the top of the circle. Why is it not the bottom? Because there's no negative on it. Right? Square root gives you the positive root. So this would be a circle centered at,
5.
no, with radius 5, centered at 0, 0, because neither one of these has minus anything. You guys are with me or not? So again, isn't this the same thing? Just with the understanding the y's can't be negative. Wouldn't this be a circle at 0, radius 5? Are you guys cool with that? You better know that on site, because I don't know, it might happen to you soon. Right? What's this? 5. You'd hope that it actually would be the, let's go such. Alright, so that's the function we're dealing with. At the point 3, now why does this make sense that the output was 4? Because the radius is 5. So I got a 3, 4, 5. Hey, that's why the output was 4 there. Holy shit. So now at that point I want to plot negative 3 fourths x plus 25 fourths. Right? So obviously a point is right there. I can plug 0 in. I get 25 fourths, which is just a little more than 6, so it's up here. And it goes, whee. And that's gross, but oh well, my scale sucks. I like how this is 5, and then this big thing is 1. Oh well. But again, if you're a little more careful on your picture, and you plot that point, you know it goes through that point, and you just plug a 0 in, you know it goes through that point, it should get pretty close to hitting that bad boy just once. Notice there's no symbol of a graphic calculator, so they wanted you to do this by hand. Okay, maybe. Are you guys with me? Some of you guys just are so barely there with me. I don't mean that in a bad way. Sounded bad, Jeff. Oh, they'll be all right. What else they ask you? One more thing they ask you to do. For what values of x is the linear approximation accurate to within 0.1? I guess they do have a graphic calculator in there. And this is that process we talked about in class where you take...
Would you just use an intercept function on your calculator?
Yeah, exactly. Yeah, you just got to be careful about getting the window to show you what you got to see. So this is where we want to know this guy is in between, where'd it go? Rad 25 minus x squared minus 0.1 and rad 25 minus x squared plus 0.1. Let's see where it's contained. So I'll have a circle that's moved down by 0.1 and a circle that's moved up by 0.1. And then I'll have the line come in. I just want to see where it intersects those. So there are several homework problems just like that. Hopefully you're able to do some of them. Anybody want to see that up here? I want to see if I can... This one should work better because the error is not quite as crazy as I tried to make it last time. Alright, so while that thing is warming up, any other questions about anything? Yes?
Can we do a related rates problem?
Yeah.
Number 24 on 3.9. It's a trough. I don't know how to draw it.
Okay, so its ends have the shapes of isosceles triangles. So you draw the isosceles.
Yeah, but is it? Oh,
It's going to be like that. That's close enough. For me, that's pretty damn good. I just do that. There's a slight error in manufacturing. There's a trough.
okay. That looks good.
What's that?
I don't know why, but I thought it was going to come out like two arrows, like pointing like this.
Oh, yeah. Obviously, you have something holding this thing up. Right, so it actually will hold stuff. Right?
Yeah.
So your pigs can come out there and eat, or whatever the hell this is for. Horses can drink. You can throw somebody in it. You're in some kind of old-style Western saloon fight. Which one was this again? 24?
24.
So the trough is 10 foot long. Its ends have the shape of a isosceles triangle. 3 feet across at the top, have a height of 1 foot. That's really nice they told you the height. They didn't have to. Blah, blah, blah. If the trough is being filled with water at a rate of 12 cubic feet per minute, what is this in symbols?
GH. No.
dV. dt. That's right, cubic feet, so that's volume. Right? We got to really be careful about units, guys. I love some of you guys are telling me the area is feet, and I'm like, no, this can't be. What is that? So your units inform you what symbols you want to use for that. If they would have said square feet, then I know that's something related to some kind of area. Otherwise, you put the numbers in the wrong place, it gets all freaky.
So I see where it's going from here. But
Well, let's do it.
So you just
How
do
fast is the water level rising when the water is 6 inches deep? So here I got my water. Straw, its own little isosceles triangle here. So this is 3 foot, and this is 1 foot. Now, are you guys comfortable enough to understand? It's a classic thing about related rates. You have something inside of this that's changing its own dimensions. So there's, what's this? H. I love it. And what's this? Maybe I'll need this. Oops, let me just do this. What is it? Who? B? Don't say V. Are you saying V?
No, B.
B. I like it. Why not? I like it. Like a base. Kick ass. It takes me a while. Thanks. Sometimes it took me a while. Show off my awesome English skills. So the problem, of course, is now here's the beautiful thing. You kind of love this about any shape that's repeated. Anything that has a repeated shape. Its formula is area of the base times the height. That's why it's a big ass B. I'll teach by 120. They finally see this. Any prism. What's a prism? A prism is defined to be a repeated shape. If you know the area of the base, you multiply it by the height. This thing's just been laid on its side there, right? So what is the area of the base? So what they told me is really nice for later, but for right now, the area of the base in general is going to be, what's the area of this? So big B is 1/2 BH. That's the area of the water, right? H2O. So 1/2 BH. Now one thing I have to be careful about. Well, it doesn't matter, Jeff. This is just 10. It's not another H. You with me? Thank God. It's 10. Right? So the volume of a prism, of any repeated shape, is the area of the base. So if you gave it a trapezoid, it'd be 1/2 base 1 plus base 2 times height times however long it is. Right? That's how it works. Big ass B times H. The area of the base times the height. Maybe. Well, we see that. What's the area? What's the volume of a cylinder? Who remembers that? The area of the base is pi r squared. That's big ass B times the height. How much is repeated? How many circles do you have stacked up? H of them. Let that be easy. Oh, we got to go back and do that one. Let's see. This is 5. And what sucks about this? B and H. And I want to know dV, and I know, what is it that I know? I forgot. Oh, I know dV. What do I want to know? That's what it is. What do I want to know? What are they asking me about? What do I have to figure out? How fast the water level rising? Yeah, dH dt. I want to know what dH dt is. Which informs me as to what I don't want in my formula. What do I not want in my formula? And as we all have learned from that quiz, if you missed it, you missed a real experience. You will not forget this now. Make your formula have what you want in it first. Right? So how do I do that? How do I get rid of B? I don't want freaking B.
relate B to H.
Yeah, I got this thing. Right? Yeah, okay, B over 3 equals H over 1. So H is B over 3. So B is 3H. So I can put 3H in place of B. Cool. And then there's it's pretty decently easy to do dV dt. Is that cool? You guys alright with that? This happens a lot.
Are you getting that from the similar triangles?
Beautiful, exactly. So it's exactly like that very first problem we did on that worksheet that I handed out. That very first problem, can't remember what it was, but it was conical, right? It was a cone. Yeah.
So it's 15H squared when you plug into VH would be?
Yeah, so you'll get 5 times, yeah, it'll be 15 h squared. Is that right? But I feel like I'm missing something. Oh yeah, because the 10 already, so that don't forget. So the 10 had feet, and then this is squared, so that's 2 more feet, so I end up with cubic feet. Good, my units match, thank God. So now I can do dBdt, and that looks yummy. That looks fine. I think you guys might even agree with my yummy assessment. That is awesome equation to have. All right, so real quick, what was that number? 102. Did I erase it? No. Good job, Jeff. Let's see. So now the idea is to wait some more. Oh, open chargers, huh? My poor Dolphins had to go all the way to England to lose. It was awesome. All right, let's see. Come on. All right, so I've got, I take the top part of the circle minus 0.1. Then in the middle I put my approximation negative 3/4 x plus 25/4. There's my line, no Jeff. And then I do square root. Plus 0.1. Oop. And of course I'm in this weird. Come on, calculator. I think I blew the calculator up. There it is. So there's my circle. There's actually 2 circles in there. Everything's happening around that point. There's the other circle. So obviously I want to zoom in here. So this tolerance is a little bit easier than the last time, so it shouldn't take too many zooms to get there. So I want to see this area here. All right, calculator. I feel like I'm out of time delay. You guys see, hopefully it's pretty obvious how I know where to zoom in. So there's the circle shifted down by 1. Here comes my linear approximation. And then here comes the circle shifted up by 1. And there you go. I can see the 2 places where it hits. All right, so my straight line approximation is not good enough back there. You guys with me? So these 2 curved things, the circle shifted